I welcome you all in this NPTEL online certification course on mechatronics. Today we are going to discuss the electrical system models. So, what I am going to talk about is this. First, we will be looking at the various building blocks for modeling of any electrical system, and then we will be seeing at the various combinations of these building blocks, okay, in modeling of an electrical system, and then we will take up an example of electrical system such as a motor, okay, and we will see that how can we model the either the armature control motor or the field control motor. Okay. So, this is what I have planned for you in this lecture. Okay. So, the basic building block of electrical system are inductor, capacitor and resistor. Okay. So, first of all let us look at inductor. We see that this is the symbol for an inductor. Okay. So, the potential difference VL across it at any instant depend on the rate of change of current through it. So, basically, so VL is L di by dt, where L is inductance, or I can write it in terms of current as 1 by L integral VL dt. Okay. So, this is how symbolically it is represented. Next building block is the capacitor over here. Okay. So, see there is a capacitor of capacitance C. The current through say is current through is say I, and say the Vc is the voltage across the plates over here. So, the potential difference across it depends on the charge on the capacitor plates at that instant. Okay. So, for here the Vc is equal to Q by C, or this is 1 by C, and Q I can write in terms of current as integral of I dt, or from here I can write I as C dV C by dt. Next building block is resistor, which basically comes from the definition of the Ohm definition for the resistor given by Ohm's law. So, here the voltage drop across the ends of the resistor VR is given by I into R, where I is the current through the resistor and R is the resistance, okay, of the resistor. Okay. So, that is there. So, here are the three basic electrical system building blocks: resistor, inductance and capacitance. Here the relationship is VR is equal to IR. Here this is VL is L di by dt, and here V is Q by C, basically 1 by C integral I dt. This equation is written sometimes in this form as I is equal to 1 by L integral V L dt, and here this is I is equal to C dVc by dt. Now, what about the energy and power? So, both inductor and capacitor store energy, and a resistor dissipates energy. So, energy is stored by an inductor when there is a current I is basically half L I square, okay, and energy stored in a capacitor is actually half CV square. I am not going into derivation of these because you must have studied these things in your earlier classes. And the power dissipated by a resistor when there is a potential drop V across it, basically here this VR is basically this one. Okay. So, and this is Vc. So, it is V into I, and this is basically V square by R. Now building up of a model for an electrical system. So after defining these three basic elements, we can build up a model for electrical system using Kirchhoff's current law and Kirchhoff's voltage law. I have discussed talked about these two Kirchhoff laws in my very introductory lecture in the first week of it. I am going to refer those laws here again, which will help us in preparing the model for an electrical system. Okay. The equation describing how the electrical blocks can be combined are Kirchhoff's law, basically the combination of these blocks. Okay. So, the first law is actually says that the total current flowing towards a junction is equal to the total current flowing from that junction. Okay. So, the current in basically has to be equal to current out at a junction, or what we can say is that the algebraic sum of current as it at a junction is 0. So, if I look at this electrical circuit over here, so if I take this junction say here, so here you can see the current in is I1 and current out is I2 and I3. So, I1 is equal to I2 plus I3, and then I1 I can write as if this voltage is V and here voltage is VA. So, V minus VA by R1 and I2 is VA by VB. Of course, we can assume this as ground. So, the voltage at B is equal to going to be 0. So, VA by R2 and I3 will be actually VA by R3. Okay. Then there is a second law by Kirchhoff, and it says that in a closed circuit or a loop, the algebraic sum of potential difference across each part of the circuit is equal to the applied EMF. Okay. Or what we can say that sum of the voltages across a closed loop or path is going to be 0. Okay. So, this law can be explained with the help of this very example over here. Okay. So, it is the same figure which I have shown you in the previous slide. Okay. So, here suppose I assume a current direction say in this direction say current I1 and in this direction say current I2. Then if I look at there are two loops, this is your loop 1 and this is your loop 2 basically. Okay. So, if I write the expression for loop 1, so it is applied voltage is V. So, this V is drop across R1. So, this is I1 R1 and drop across R2 will be basically this resistance is R2 and the net current flow in this direction is going to be I1 minus I2, because in this loop this is going to be the I2 and this is going to be the I1 actually. Okay. So, the net current will be in this direction will be I1 minus I2. Okay. So, this is the Kirchhoff's voltage law for the first loop. Likewise, I can apply it for the second loop. So, for the second loop there is no source over here. So, this left hand side is 0, and if I write the drop across R3, so it is I2 R3. Okay, and then the drop across R2 in this direction basically. So, it is I2 minus I1 times R2. Okay. So, this way I can write the Kirchhoff's voltage law for the two loops. Okay. So, these are actually the building blocks for us if we want to model an electrical system. Okay. So, we have seen a resistor, we have seen a capacitor, we have seen an inductor. So, now I am going to take the various combinations of these say which exist in a circuit. Okay. So, here suppose I have a combination of resistor and capacitor. Okay. So, say there is a circuit, you have a applied voltage source, a resistor and a capacitor is there. So, this is my input and say output I want to take across the capacitor, that is Vc. Okay. So, I can apply the Kirchhoff's voltage law. So, this V will be actually VR plus Vc. okay, that is voltage across resistor and voltage across capacitor. For VR I can write just equation as I into R, because it is an it is a resistor, and for capacitor this V is Vc is actually Q by C, or it is integral I dt by C. Okay, so I get I as C dVc by dt, and now I can substitute here. So this V actually can be written as IR plus Vc, and this I can substitute over here. So this is C R dVc by dt plus Vc. So as I said, my aim is what is my input here? Input is my this voltage, and what output I am looking for? Output I am looking for is Vc. So forcing function here is this, the voltage supplied, and the right hand side you can see that it is a differential equation of the first order. Okay. So this way I can derive the system equation for this system, which is consisting of a resistor and a capacitor. Okay. So next let us take the example of the resistor and inductor. We have seen resistor, capacitor and inductor. So last slide I have shown you the example of resistor and capacitor. Next let us see an example having combination of resistor and inductor. Okay. So say you have a resistor and you have an inductor over here. Okay. So again my input is applied voltage V, and output suppose I want to take across the two terminals of the inductor, that is my output. So again I can apply the Kirchhoff's voltage law over here. So my V is equal to, this is my VR and this is my VL. So V is equal to VR plus VL over here. Again VR I can write as IR. Okay. So this equation I can write as IR plus VL, and for VL you see VL is simply L di by dt, or I can write I is equal to 1 by L VL dt. Why I am writing it in this way? Because I want things to be expressed in terms of the output parameter, that is VL. Okay. So my expression is V is equal to VL, this is already there, and here I can substitute for this I as 1 by L VL dt, and R is already there. So this is my equation. Okay. So now here also you can see that this is my left hand side here. So this is my forcing function, which is the input voltage, and the right hand side I have got the VL as the parameter. Okay. So this is that is the voltage across the inductor. Now next example let us take where we have a combination of R, C and I. Okay. So I have got a resistor, I have got a capacitor, and I have got an inductor, and suppose my output I am interested in seeing across the capacitor. Okay. So this is my applied voltage or the voltage source, and say here I is the current through the circuit. Okay. So basically what my intention is? My intention is to develop a relationship between Vc and V. Okay. And I have seen it is a second order differential equation. Okay. So this is how it looks like, but how it comes, let us see that. So if I apply the Kirchhoff's voltage law over here, so my V is VR is here, VL is here, Vc is here. So V is VR plus VL plus Vc. VR I can write as IR, and VL is L di by dt. So I can substitute that in this one. So this is what I get, IR plus L di by dt plus Vc, everything I want in terms of Vc. So I will write everything in terms of Vc. Okay. So you see I is equal to C dVc by dt, this relationship I know for a capacitor. Okay. So I can substitute for the I over here. So this is what I get. So, VC, this VC is already there, and this RC dVc by dt, this is if I substitute I in this one, and if I substitute for I here, then I get this one. Okay. So, it is a basically left hand side you can see the forcing function is the voltage supplied, and the right hand side we have got the VC. Okay. So, it is a second order differential equation for the RLC circuit. Okay. If we have a resistor, inductor, capacitor system here, in the previous case all these RL and C they were in series, and suppose here they are in parallel, resistor, inductor and capacitor are in parallel. Okay. Then in this case we can make a nodal analysis using say Kirchhoff's current law basically. So, at this point we can see that I1 is equal to I2 plus I3, and I1 I can write as V minus VA by R, I2 is basically C dVA by dt, and I3 is basically 1 by L VA dt. Okay. And Vc is actually same as Va. Okay. So, that is there. So, I can substitute values of I1, I2 and I3 in this equation. Okay. So, I will be getting this equation. Okay. So, this way using KCL and KVL we can write equation of the system. Okay. So, you see often there is an analogy which is made between the electrical system and a mechanical system. Okay. So, we have seen the mechanical system in the previous lecture. Okay. So, where you have a mass, you have a spring and you have a damper over here. Okay. And its analogous electrical system is RLC circuit basically consisting of a resistor, inductor and the capacitor. So, see for a resistance from Ohm's law we get I is equal to VR for electrical system, and for mechanical system for a damper F is equal to CV, where C is the damping coefficient basically, V is the velocity of the damper and velocity of the piston inside the damper, and F is the resistive force basically which is going to act. So, if I take a comparison of that, so you see that this C is analogous to your 1 by R over here. Okay. So, damping constant C is analogous to 1 by R in the electrical system, and your force in the mechanical is analogous to current in the electrical. So, force in mechanical is analogous to current in electrical, and velocity in mechanical is analogous to the voltage in electrical. Velocity in mechanical is analogous to voltage or potential difference in electrical. Okay. And inductance is analogous to spring, and capacitance is analogous to mass. Okay. So, this way we can make an analogy between the electrical and mechanical system. Next, before we take an example of further example of a motor, let us look at the little basic of say electromechanical system. These devices such as say potentiometer, motor and generator transform electrical signal to the rotational motion or vice versa. Okay. So, what does a potentiometer does? Basically it has the input of a rotation or linear motion and output of a potential difference. Okay. And electrical motor, it has input of potential difference and output of rotation of the motion of the shaft. In a generator, it has input of rotation of the shaft and output of the potential difference. So, these are the 3 examples of the electromechanical system. So, now let us look at a little concept of the DC motor, and then we will see that how can we use the basic building blocks in deriving the system equation for the motor. Okay. That is the armature excited as well as the field excited motor. We will be seeing the both cases. Okay. Now, in mechatronic system, electrical motor are often used as actuators, we have seen that. Okay. And they are mostly used for in the position or speed control system, and the basic principle of operation of a motor can be explained with the help of this figure. Okay. So, basically here is that if a current carrying conductor is placed in a magnetic field, basically it experiences a force. Okay. So, that is the basic principle. So, a force is exerted on a current carrying conductor placed in a magnetic field. This is basically Lorentz law, and this force called Lorentz force is given by BIAL, where B is the strength of the magnetic field, IA is the current through conductor, and L is the length of the conductor. Okay. And then the second law is basically Faraday's law, which says that when a conductor moves in a magnetic field, then an electromagnetic EMF is induced across it. Okay. And the induced EMF is equal to the rate at which the magnetic field magnetic flux swept through it by the conductor changes, okay, or very popularly known as E is equal to minus d phi by dt, and this negative sign actually indicates that the direction of voltage induced is opposite basically. Okay. So, that is the negative sign because the EMF is in such a direction as to oppose the change producing it, and which we call it as the Lenz law. Okay. Okay. So, that is the direction of induced EMF is such that it produces the current. Now, this current sets up a magnetic field which basically tends to neutralize the change in the magnetic flux linked by the coil and which was responsible for this EMF. Okay. And that is why this potential is often called as the back EMF. Now, from the Lorentz law, the force with n wires can be given as n BIAL, and so the torque, if this is having a width B basically, okay, then you are going to have the torque as F times B, and this F is NBIAL times B. Okay. So, here basically what I am saying is this N is constant, say field strength is constant, okay, L is constant, B is constant. So, your torque produced is proportional to the current through the armature, okay, other parameters being constant. Okay. So, here suppose if I am taking that B is also not constant, then we can take that the torque is proportional to B times IA basically. So, this is my equation, T is equal to K1 B times IA. Okay. And you see that this back EMF is proportional to the rate of rotation of the armature and the flux linked to the coil basically. So, this VB is equal to B omega basically, and this K2 is constant. Okay. So, we will be using that concept for the. So, here let us see the DC motor with armature and field coil separately excited. Okay. So, here this actually indicates the schematic of the DC motor. So, you have the armature conductor over here, and you have the field coils basically over here. Okay, and this is your armature. So, here if you model it, so we have the armature circuit which is modeled as a inductor resistor. Okay, this is the back EMF, and you have a load over here. Okay, and this is the field circuit modeled as the RF and LF. and this is the field voltage basically. So, first we will be looking at the armature controlled motor, and then I will be talking about the field control motors. Okay. So, in the armature controlled motor, this type of motor field current is held constant, okay, because we are controlling it through the armature, and the motor is controlled by adjusting the armature voltage VA, this one. Okay. So, a constant IF actually means the constant B. Okay. As I said that we are taking IF constant. So, our constant field current means a constant B. So, our VB is equal to K2 B omega, B is constant. So, I can take these two together constant. So, this is K3 times omega. Okay. So, then I can apply the Kirchhoff's current law, Kirchhoff's law over here, KVL, Kirchhoff's voltage law. So, the net voltage is VA minus VB, and this is voltage across the inductor, and you have voltage across the resistor. Okay. And then I substitute for VB K3 omega over here. So, this is the equation which I get. Okay. So, the current through armature generates the torque, and since armature is since for an armature controlled motor B is constant. So, our T is equal to K1 B IA. So, I can take K4 IA, and this K4 I can call it as the constant, okay, the torque constant of the motor, and this torque is actually the input for the load system. Okay. And if we neglect the torsional effect of the shaft RB, and if RB is the bearing resistance, then net torque acting on the load is basically T minus RB into omega. Here this you have a load here, and there is a torque T, okay, and the resistance in the bearing will be actually RB omega over here. So, we have this, and this net torque is going to be responsible for the angular acceleration of the load. So, this is I d omega by dt is equal to K4 Ia minus RB into omega. Okay. So, in case of armature controlled motor, so we have got the two relationship, this relationship which we have applied the Kirchhoff's voltage law for the armature, and we have got, and this relationship we have applied for the load. Okay. So, this we have got. Okay. So, here we can substitute for Ia in the second equation, okay, from the first in order to get the relationship between the input voltage VA and the output omega. Okay. So, these two equations we can use to get the relationship between our forcing function, which is the input voltage VA, and the output omega of the motor. Next, let us take the field control motor. Okay. So, in case of field control motor, basically we are going to change the field over here. Okay. So, in this type of motor, armature current is held constant. Okay. So, the motor is controlled by varying the field voltage. Okay. So, for the field circuit here I can write this equation, that is Vf is equal to, I can write the KVL basically over here. So, Vf is equal to If Rf plus Lf dIf by dt. So, this is for the field, okay, field winding rather. Okay. So, that is there, and the field current leads to the production of a magnetic field, thus a torque act on the coil basically. Okay. And this torque is given by K1 B Ia. Okay. Now, here as I said K1 Ia, I am keeping constant, armature current I am not changing. So, this is this together I can take it as a constant. So, this is K5 into B, Ia is a constant. So, T is K5 into If, since B is proportional to the field current IF. Okay. So, if I neglect the torsional effect in the shaft, net torque is again going to be equal to T minus Rb into omega, where Rb is the actually the bearing resistance and omega is the angular speed of the shaft. Okay. And this is the factor which is responsible for the acceleration of the shaft. So, I equate it to I d omega by dt, and then I substitute for T, that is k phi pi f minus Rb omega. Okay. So, this is what I get, this is my load equation. Okay. So, I d omega by dt is k phi I f minus Rb omega, and this is my relationship which I have got from the field winding. Okay. So, the output is omega here and our input is Vf. So, this is basically my output and input is my Vf basically. Okay. So, we can eliminate IF actually. So, IF is the common in these two equations. So, I can eliminate IF from the above two equation and get a relationship between the output which is my omega and the input which is my Vf. Okay. So, you see that here we have used the basic building blocks, okay, to model both the field control DC motor as well as the armature control DC motor. Okay. So, in this lecture we have seen the basic building blocks for the electrical system, and then we have used the combination of blocks to analyze a system, and then we have used the same concept of combination of block to analyze the armature controlled and the field controlled DC motor. Okay. So, these are the references. If you want to read it further, please go through them. Thank you.